Hi everyone. In this video, I am going to explain the concept of connectedness in topological spaces. Let couple X be a topological space. Then X is called as separated if X is the union of two disjoint non-empty open subsets of X. That is, if U and V are two disjoint non-empty open subsets of X, and if X equal to U union V, then capital X is called as separated. The space X is said to be connected if it cannot be expressed as the union of two disjoint non-empty open subsets of X. That is, if X is not separated, then it is called as connected space. In example 1, I am given this example for separation. Let Y is the union of two intervals. That is, the first one is right open interval minus 1 comma 0, and the second one is left open interval 0 comma 1, and it is a subspace of the real line capital R. Now the first interval right open interval minus 1 comma 0 is non-empty, and the second interval left open interval 0 comma 1 is also non-empty, and both are disjoint. Hence we can say that Y is the union of two disjoint non-empty open subsets of capital Y. Therefore we can say capital Y is separated. In example 2, connectedness is given. That is, suppose if we take the space capital X as closed interval minus 1 comma 1 of the real line capital R. Now the subspace capital X of capital R is expressed as union of closed interval minus 1 comma 0 and left open interval 0 comma 1. Here X cannot be expressed as the union of two disjoint non-empty open sets. Hence we can say closed interval minus 1 comma 1 is connected because it cannot be expressed as the union of disjoint open intervals. We can express minus 1 comma 1 as union of closed interval minus 1 comma 0 and left open interval 0 comma 1, or right open interval minus 1 comma 0 union left closed 0 comma 1. In both cases one of the interval is not open, hence we cannot express closed interval minus 1 comma 1 as union of two disjoint non-empty open subsets of capital X. Hence we can conclude that this interval, this closed interval minus 1 comma 1 is connected. That is, capital X is connected. Next we are going to see lemma. Statement is, if the sets capital C and capital D form a separation of X, and if Y is a connected subspace of X, then Y lies entirely within either C or D. We are given capital X is the union of two disjoint non-empty open sets capital C and D. Because X is separated, let Y is a subspace of X. Hence the sets C intersection Y and D intersection Y are open in Y. Because C and D are open and Y is a subspace of X, C intersection Y and D intersection Y are open by the definition of subspace. Now if we consider their union, that is C intersection Y union D intersection Y, we write this union as C union D intersection Y, but we know that C union D is capital X. So capital X intersection Y. Since Y is a subspace of X, X intersection Y is equal to Y. So Y can be expressed as union of two open sets C intersection Y and D intersection Y. Now if they were both non-empty, that is C intersection Y and D intersection Y were both non-empty, and we know that both are disjoint because C and D are disjoint, C intersection Y and D intersection Y are disjoint in disjoint and open sets. We know that both sets are disjoint and open sets, and we have to check the only concept of non-empty. Suppose if two sets are non-empty, then we can say both are non-empty, then we can say that capital Y as separated by the definition of separation. But we are given Y is a connected subspace of capital X. So one of the sets C intersection Y, D intersection Y must be empty. Hence, one of the sets is empty implies Y completely contained in either C intersection Y or Y completely contained in D intersection Y. Implies we can say that Y completely contained in either C or in capital D. So Y is either a subset of either completely contained in C or completely contained in D. Next theorem is the union of connected subspaces of X that have point in common is also connected. So we have to take a collection of connected subspaces of X and we have to construct their union and let capital Y as union of connected subspaces of X, that is Y is equal to union of A alpha. Now our claim is to prove Y is also connected, that is union of connected subspaces of X also connected, having a point in common is also connected. Let P be a common point of union of A alpha. Then if Y is separated, suppose Y is separated, then by the definition of separation we can write Y as union of two disjoint non-empty open sets C and D. Then P belongs to, we are taking P as the common point of all connected subspaces A alpha. Therefore P belongs to union of A alpha also. So but we are writing Y as C union D. Therefore P belongs to either C or P belongs to D. Suppose P belongs to C and we know that P belongs to A alpha for every alpha, and we know we are given each A alpha is connected. So P belongs to either C, P belongs to C implies P belongs to A alpha, and so A alpha completely contained in either C or capital D. Because A alpha, P belongs to capital C, A alpha completely contained in C and it cannot lie in capital D. So A alpha contained in C for every A alpha. So union of A alpha also contained in C, which implies that capital D is empty set. But we are assuming Y is separated and so both C and D are non-empty sets. But here we get D as empty set. This is a contradiction to our assumption that Y is separated, and so we conclude that Y is connected. Next theorem is the image of a connected space under a continuous map is also connected. So let us define a mapping, a continuous mapping F from capital X to capital Y. Let us assume that capital X is a connected subspace and our aim is to prove that its image, that is f of X, is also connected subspace of capital Y. Let f of capital X as capital Z. Now our aim is to prove capital Z is also connected subspace of capital Y. Now let us define the mapping G as X to Z, that is we are restricting the mapping F from Y to Z, and so G is also continuous and it is also a surjective mapping by the definition of, it is continuous by the definition of continuous mapping, rules for continuous functions. And since we are taking the codomain as Z, which is the image of capital X, we can say that G is surjective also, and our aim is to prove Z is also connected. Suppose if we assume Z as separated, then by the definition of separation, we can write Z as union of two disjoint non-empty open sets A and B. Okay, so A and B are open subsets of Z, and since G is continuous, its inverse images also open in capital X. That is, G inverse of A and G inverse of B are open in capital X. And if we consider their union, G inverse of A and G inverse of B, we get the domain capital X, because G is surjective. G inverse of A union G inverse of B is equal to capital X. So X is there. Here G inverse of A and G inverse of B are disjoint open sets and disjoint non-empty open sets, and so we can say capital X as separated, but we are given capital X is connected space. So this is a contradiction or assumption that capital Z is separated. So our assumption that Z is separated is wrong. So the image space Z is also connected. So the image of a connected space under a continuous map is also connected. Thank you.